Okay, hello everybody. The last of your presentations, I think I did the first one 10 days ago, was it? In this room. It's really hot and sweaty, so we're going to go really fast. My name is Michael Weinstock. These are my friends and colleagues, George Dronamides, Evan Greenberg, and Meron. You can see our CVs and backgrounds on either on our Facebook site or on the MTech micro site. We each have specialisms, but we do everything together. So my particular interests are in natural systems and emergent and complexity sciences and in genetics. George is the father of biomimetics, the first chair of biomimetics in the world, a structural engineer by background, but that doesn't stop him being an expert on architecture and urbanism and everything else. Learn. Evan and Meron are graduates of MTech and have been with us, I think, 5 years and 4 years. And they have developed their own specialisms, and they'll say something about it. We start work on Friday morning at 10:30. So the next 10 minutes or so is just going to be a little overview of the structure of the year. I'm not going to explain the philosophies and backgrounds and all the people that are coming to see you. Okay. All of that happens. I explain all of that on Friday, and on Friday afternoon you will see 4 projects from the graduating MSc groups, and later on in the term you'll see the MArch groups. So today is just the overview of the structure. That's us. At the bottom we have the principal visitors. We have a masterclass series which we've been running for a number of years. We have long-term relationships with them. Some of you will know Francis Ace, you may not know. He runs the advanced group at Foster's, which used to be the special modeling group, son of Robert Aish, computer science by background, scientist by background. Akim, most of you will know a little bit about his work. It's very well published and on the net. Christina and Ephraim, we've been working with them for 3 years, I think. They have just finished their second building in Madrid, very large and very good building. Hasn't been published yet, and you will be the first to see the kind of detailed design and the approach of that building. Wolf is now a partner of Borough Happold and director, has also been with us since the foundation of MTech. And like most structural engineers, he thinks he knows more about architecture than we architects do. Jordi Trucco is another graduate of MTech. He's been running his own master's program for a number of years in Barcelona. He was the first of our students to get a 2.3 million euro grant for the development of the project that he did in MTech, which is now been through the EU grant process, and he'll be showing the final finished prototype, which you will be able to see. So, okay. Here's how we're organized. The boot camp is very important. For us, many of you have different skills, and we try to choose people to come to the program with different backgrounds. But we want to make a fresh start, so we want you to leave everything you know behind. We want to start again with making clean geometries. I'm going to ask Evan to go through that in a little minute. There are 2 studios, 1 each term, each with a different agenda. And there are 3 seminar courses. Now the seminars are different to the ones you might be used to. We give lectures, and there are theories and there are papers and things to study, but you will design and do experiments and produce a design at the end of each seminar. So these are seminar series that need a lot of engagement from you. It's not a question of sitting back and making notes and then chucking out an essay. You have to demonstrate that you understand the principles and the knowledge, and you have to put it to work in a design. design build. We build something every year, or rather you do, and these guys do, and I stand and clap and try and fiddle around a little bit, try not to be too much of a nuisance. We've been running a series of experiments for the last 3 years on, which we'll talk more about, but really on how you get advanced performance from very ordinary materials. And that comes through combinations of simple materials, but also through the geometries. And we have our own kind of build up of knowledge of that. And then the dissertation, which I'll say something briefly about at the end.
So you'll hear a lot of me in the next few days, so I'm gonna run through this pretty quickly. But bootcamp, which you'll start on Monday morning, is a 3-week super intensive workshop where we basically will equip you with all of the material and digital computational skills that you need. And so we'll start teaching you just simple grasshopper, kind of giving you the knowledge to be able to then develop your own skills through that. But essentially the idea is to design a component-based system that will be self-supportive as a surface in the studio. So you will design it, you will build it yourselves. You'll do this in 3 weeks. It'll be super intense, but it's fun. We'll try to help you understand how to deal with materials and understand the inherent material properties of all sheet materials. It's all you can use, at least at first. And how you can couple material constraints, material properties, structural performance, and geometry. So just some examples from years past. We have to understand how to fabricate these things. How do we join them? George will probably talk later when we discuss the biomimetics course, that joints are the bane of all architects. But we have to deal with it somehow. Again, we try to, as Mike said, we try to teach you how to deal with geometry from the mathematics side, so that you have a clear understanding of how to generate clean geometry. And we'll also teach you how to model geometry for different types of analyses and different types of methods. And so this is a good example, I think, of what you'll sort of end up with at the end of your 3 weeks is some surface structure that will be supported at 3 points in the studio. And the rest is kind of up to you. But we'll get started again on Monday. So we'll talk more to you about it on Friday. But it's an intense 3 weeks, but I think we'll bring everyone up to the same level as Mike said. So whether you know Rhino, Grasshopper, Maya, whatever you came with, we kind of use the same tools just because that's what is kind of, let's say, the community out there is strongest. So we generally work in the Rhino platform. We'll teach you Grasshopper. Later on in the year, we'll bring in other plugins. We get into Python, et cetera, et cetera. But we'll take you from the beginning, 0. Don't worry if you don't know anything. We'll bring you there. Yeah, so.
We like science. We like maths. We like biology. We like computation. And particularly, we like materials. And we don't see any reason why architects can't be good at that. George and I spend a lifetime studying different aspects of biology. And these two guys in 5 years have gone a long way with their own specialisms. Core 2, you're taking something from bootcamp, similar kind of thing. It's a component system. You have to develop it to the scale of a pavilion, but it has to do something. In this particular case, these are small timber devices for catching water, and as the water accumulates, the weight changes, the curvature changes, and it's able to move and shed its water. And you can see a little bit of the experimentation and the summary there. Okay. And we also like to look at these analytically. We teach all of the high-end analytical software. George particularly is a specialist in this field, and Evan. And you'll be very familiar with every kind of computational analytical tool, engineering tools, by the end of the first term. We teach it in 2 different ways, and I'll come to that in a minute. But this is typically, we don't do kind of make a big deal about renders and so forth, but we like a little bit of it. but this is the array of those systems, mainly described in the final output as a series of spaces, but also from the performance, which is critical for us. We look at a number of engineering systems, but again, we try to teach them in a creative way and ask you to engage in them creatively. So again, tensegrity is something you can learn much quicker with your hands. Once you understand the principles with your hands, you can understand the mathematics, and we work in these kind of iterative cycles between physical experimentation and computational experimentation. We use a lot of algorithms. We like algorithms. They're really fun. They are a different way to think about design. But by themselves, they're not much good without a design intention and without clear architectural ambitions. These are some of the outputs, which you see again. I think the physical model actually came first. Algorithms were developed from that, and then was a further iteration. This is actually a huge model. So we like to see a lot of physical modeling as well as mathematical modeling. And the two, we teach you how to work those two things together. The analytical tools we do apply to both to prototype materials so that we can understand some of their behavior, but we calibrate, or we learn to calibrate these kind of softwares from physical behaviors that we measure. So again, you don't just become kind of software jockeys that are good at these analytical softwares. You understand their limitations, but particularly you understand what these columns on the left mean, and how to manipulate them, and how to calibrate the software to produce and investigate the kind of areas that you're interested in. As you can see a little bit from the exhibition. Biomimetics, again, is a seminar course that is led by George. It has a theoretical component, but it also has a series of investigations and experiments.
Yeah, I mean, the idea of introducing the biomimetics aspects have got to do with the fact that it's a growing way of thinking about design. It started in material science, it spilled over in mechanical engineering, and is growing very, very rapidly in a lot of fields, and architecture, not surprising, is involved as well. And if you look at what's going on now, you will see there are groups, people, research units in the States, in the UK, ourselves, Germany, Netherlands, Italy, Spain, the Far East, in China, and whatever not. So things are happening, and the idea behind is really that biology has already done a lot of good design as a result of evolution. So to shut our eyes and say, look, there is nothing interesting and nothing useful out there is really pretty arrogant. There are a lot of solutions, and it's not just looking for solutions, but also looking at the way in which these solutions are arrived at. One of the main issues about biology is the fact that organisms can adapt. That is the key issue, okay? Climate changes, temperatures go up, water increases or decreases, organisms are forced biologically, genetically, phylogenetically to adapt themselves. And what we see as the result of this evolution is a combination of geometry, form, shape, materials, growth, adaptation, response, sensing. All these things are very highly integrated. And what we want to do in the MTech with the biomimetics course is really to open up your minds more than anything else. Okay, we are sometimes lucky in that we do find specific solutions which we can translate into technical solutions, but to a large extent is really to develop a way of thinking, a way of approaching an architectural design process using biology as a kind of model system. I don't know if we've got any more. This was a branching system, which was one of the mini projects in the seminar series of biomimetics, looking at distribution of fluids. And branching system exists in the blood vessel system or in plants, which have to distribute water right, left, and center. Root system, branching systems, all these things have got a logic. The geometry of these things is not just random. They are the response to a set of inputs. The inputs come from the environment, the response is the biology. These are seed pods of various kinds, which can change shape, feathers, active plants of various kinds. And the idea is behind, again, is to extract the basic fundamental design principles, not to replicate biology. Okay? I mean, it would be foolish to try to do so. On the top left, you got the Venus flytrap, which is one of these carnivorous plants. Okay, we'll talk about that in more detail during the course. And what you see below is really the interpretation, or the reinterpretation, if you like, of that biological system from one of our group of students, where you got a group of cells organized in particular fashion. So geometry is very important, material is very important, pressure, forces, and whatever not, and you can create some responsive systems which have got a logic within an architectural context. This was a bridge. This one started again from a long way away back into the biology, and to a large extent the success of the projects is due to the fact that at the end of the process, when we see the final architectural thinking, we are really very, very far away from the original biology. In other words, we don't see what started the process. We see the result of the process. This is a nice one which we had on cacti, which have got a number of interesting functions. They store a lot of water. They can adapt to the very harsh environments, of course. How do they work? Not only at the local level, material level, but at the global level. How do they respond? And then how you translate this information into some architectural thing. This is one of the projects we had with the type design and build, so I leave back.
So you will have seen the biomimetics runs alongside Core Studio 1. So you're working backwards and forwards. I'm going to just very quickly go through. We have quite a long background in construction. What we do, these are very, very simple plies that we made our own composite material with this, simple plies with the interlayers, fiberglass. Again, the principles from biomimetics of getting the geometry right induces different kinds of behavior in the material, goes beyond what we think of as its normal capacities, and we like to do it at full scale, as big as we can. And last year we pursued this down at Hook Park, and this is the first, the ones where we were working with carbon fiber and plywood. And we'll be advancing that, or you will be this year, where we'll be embedding more functionality, more sensors and more reactive systems within these kinds of structures. Okay, Emergent seminar again is based on biology, but on the genetics. And what you learn from here, which you, by the time you start this in the second term, you'll be fairly familiar with. You work in populations. You don't work with a single inspirational design, but you work through systems and populations. You learn how to manage all the data for this, which is a really big task. And we do all of this computationally by hand. No scripting or coding at this point. So you learn how to be computationally efficient, really, really lean. What are the minimal number of efforts or strokes that you can make? What's a minimal amount of data that will produce families of forms? Okay. We have one or two that are more advanced. This one was scripted, again working now with its own genome and sets of genes to produce a family of variant forms related to both programmatic clusters, which you can see here, volumes from that, and then the array of variations. This year in Emergence, you will be evolving urban blocks. This, we will tell you a little bit more about later, is, as far as we know, a model of the densest block that humans ever made. It's the Dark City, and I was privileged to see this as a child. It doesn't exist anymore. We also look at the so-called leading examples of designer blocks. There'll be a number of them. We're going to give you 8. You will study those and you will breed them. That also leads straight into the second studio of phase 1, core 2, which is about urban systems. 1 or 2 quick examples here with various kinds of programs. By now you're kind of computationally ambitious, let's say. You have a lot of skills, and we encourage you to be very experimental. But again, the problem, what we want you to absorb is how do you calibrate those? And we do that by tissue sampling, and we have a number, but you would also be doing these kind of tissue samplings of urban tissues from around the world in different climates, and you'll be learning how to analyze them and particularly produce the data for them. Okay. And this is the output. This was done at a dissertation level, but this is typically longer term output from developing those kind of skills. This has been widely published. This is a core 2. Again, we have ways to use a number of analytical softwares, and Evan and Meron have been working on links so that you can embed those in real time in Grasshopper and Galapagos. And we think we have some interesting protocols that I don't think anyone else is quite doing yet. So both of those will be heavily involved in this. We also look at a number of hydrological conditions as well as sunlight and so forth. So we love algorithms, but we want them not to just run for their own sake. We've also done quite a lot of work, and we want to be more ambitious this year on how you embed social and cultural spatial values into an algorithm. This is one of our first ones, but you will see we have a number of publications, and one in particular which I'll talk a little bit about on Friday, where this is our new ambition within Core 2, and we have had some successes with it. This is for arid cities, and we have some others. We like to publish. This is a minimal set. We don't teach from these, but we do invite you to read them. All of them have some of MTech student work in, but they also are theoretical background as well. So at the end of the second term, we enter the thesis formation. It's a process. You work in teams. We like mixed teams, MSc and MArcs together. So the best teams are ones, and you will see some of them on Friday, where the MSCs, 2 of them would resolve as much as possible the material science and the systems of their architecture, and their 2 colleagues would carry on with them and resolve at a larger scale the architectural consequences of those systems. We offer only 3 topics. You can see them outlined there. Active material systems, that is material systems that do something more than just stand there. They're capable of active responses. You can feel the temperature and the humidity in this room. There's practically sweat condensing on the walls. An MTech project would be, how do you use that heat and moisture? How do you get rid of it? How do you use it to make ventilation, to make a better place, and so forth? We have also had a number of dissertations on ecological systems, redesigning shorelines and deltas, and we have a very good one to show you on Friday for flood conditions in Bangladesh. And urban system design, we work particularly with emergent biomes. You can say generally there are 2 projects involved with the contemporary city. One is the mature cities of Europe and America and South America and China. But one are the new cities in places that at the moment it's very, very difficult or impossible to live. And we're particularly interested in these emergent biomes. These are the places we think where climate change and the rapidly expanding populations of the world, these are the places where new cities are going to be built. Some already started, and this is one of our interests. So, thank you. We're now almost ready for the drinks, and big smile from our director here.